Hey everyone, today we're going to start our discussion of gases, and in particular we want to look at two properties. We want to look at the pressure and the temperature of gases. So let's start with pressure. Pressure very simply is defined as a force over a unit area, and to get a sense of this, let's imagine that you're out and about and someone accidentally steps on your toe. If they were wearing this blue tennis shoe on the left, that force of them stepping on you would be spread out over a much greater area than if they were wearing, let's say, this stiletto over here on the right, and that force would be concentrated just in that very small area under the high heel. So that's going to hurt quite a bit more. So how does this idea of pressure relate to gases? Well, in gases, if they're in an enclosed container, which I've drawn down here in the black cylinder on the bottom, those red gas molecules exert pressure based on their collisions with the walls of these containers. And so the energy of those collisions, aka how fast we're moving, as well as the number of those collisions, and bear in mind these gas molecules can move any direction they so desire, the number of collisions with the wall of the container, in addition to the energy of the collisions, aka how fast they're going, dictates the pressure that's going to be exerted on that container. So if you imagine that black cylinder is actually a balloon, if you can get the gas molecules moving faster by heating them up, or if you can have more collisions, perhaps more gas molecules, you're going to exert more pressure on the walls of that container. So we can actually see this in our atmosphere. Atmospheric pressure is a result of all of the different gases that make up the atmosphere that surrounds us and allows us to live, right? So that's about 78% nitrogen, 21% oxygen, and 1% just other gases like carbon dioxide, neon, argon, helium, hydrogen, things of that nature. And all of those different molecules are bouncing off one another constantly, and they're bouncing off the surface of the Earth. And as they're doing that, it creates pressure. Now, if you go to a higher elevation, and let's make this kind of a crazy example, let's say that you go up to the top of Mount Everest, right? You're really, really high up there. Then there are a lot fewer gas molecules up there, a lot fewer gas molecules, a lot fewer collisions. That means that you're going to have a much lower pressure, and we're going to see some interesting applications of that as it relates to things like boiling water down the road. So how do we measure this pressure? Well, there are several different units assigned to pressure. There are things like atmospheres and something called millimeters of mercury, and a unit called Pascal, and a unit called torr, and one that we might be familiar with, pounds per square inch, right, which is also abbreviated as PSI, and this makes sense because it's a force, pounds, over a unit area, square inch. So it turns out we can relate all of these, and you have this on your note guide, but it turns out that there are numbers down here that allow us to convert from one pressure to another, and these are just definitions. These are things that you can employ in different problems to ensure that you know the number of each type of pressure unit as it relates to another one. So how do we actually measure these types of pressure? Well, one thing that you may have heard of is called a barometer. So people who are predicting weather use a barometer because a barometer allows us to predict atmospheric pressure. So how does it do that? Well, a barometer has some pool of some liquid. It used to be mercury. Sometimes it's an alcohol now, but basically there's this exposed area of mercury, and atmospheric pressure is able to push down on the mercury. And as it does that, it forces mercury up this tube, and as you see the mercury go up the tube, there are lines on the tube, right? It's graduated. And as you can see whether the mercury goes up or the mercury goes down. And that tube is typically graduated in units of millimeters. And because it's mercury going in there, we have units of millimeters of mercury. So if you were on the last page and you were wondering why a distance, millimeters, is the same thing as a pressure, it's because of something like a barometer, where you're measuring the change in millimeters of this mercury. Just a side note, if we're predicting weather, it turns out that high pressure doesn't really have anything to do with temperature, but high pressure means fair weather, good weather, whereas low pressure means stormy weather. So meteorologists can look to a barometer, and if they realize they have a really low pressure system coming through, then they can predict that it's going to have some unpleasant weather associated with it. There's an old device called a manometer, and a manometer was used to measure an enclosed region of gas, and we're showing this to you just because it's something that you might see in literature. Gas is measured with a manometer, and basically as you allow the gas to come out of this container over here that I've circled in green, it can push down on mercury, and the mercury is also exposed up here to the atmosphere, and so if the gas pushes more on the mercury, then the atmosphere pushes on the mercury, then you know that there's a higher pressure in the gas than the atmosphere. But manometers are very rarely used, so we're actually not going to do anything with manometers. We just want you to know that they're out there. We would look more to something like a tire gauge, right? So a tire gauge you might have used on a tire, right? A bicycle tire, a car tire, or you might be using something to check the inflation of like a basketball. And the important thing that we want you to recognize with a tire gauge is that tire gauges, or gauges that measure enclosed gases, measure the pressure above atmospheric pressure. So one of the standard tire gauge pressures is PSI, and it turns out that normal atmospheric pressure is about 14.7 PSI at sea level. And so let's say that you have a ball that needs to be inflated to 10 PSI, right? So you have this football. That's a terrible football. You know what, let's make it a basketball. That'll be easier. So we have a basketball. This basketball needs to be inflated to 10 PSI. Well, if you inflate that thing to 10 PSI, this is PSI. If you inflate that basketball to 10 PSI, and you have 14.7 PSI pushing down on that basketball from all around it, you're going to have a flat basketball, right? There's more pressure pushing down than pushing out. So really, what this gauge is measuring is the number of pounds per square inch above 14.7. So if you want to actually know the pressure inside of this ball, it's really 24.7. It's 10 psi above normal atmospheric pressure. So really in the ball there's 24.7. We have 14.7 pushing in on it. We have 24.7 pushing out, and the ball stays inflated. But gauges measure, if you would actually put that ball up to a pressure gauge, it would simply measure 10 psi because it's been equilibrated to know that standard pressure is 14.7 psi, and it's going to measure above that. So we're really measuring 10 psi above normal atmospheric pressure. And obviously, because atmospheric pressure can change in different elevations, then the pressure that you need to inflate a ball to in different regions, let's say at high elevation like Denver, might change slightly based on the atmospheric pressure pushing down. So one other thing to think about when we're talking about pressure is this idea of STP. So STP is a term you're going to hear us use a lot. It means standard temperature and pressure. And so in order to kind of have a reference point to compare experimental results to, we've defined something called standard temperature and pressure. And so standard temperature in scientific literature is 0 degrees Celsius. And standard pressure is 1 atmosphere of pressure. So if ever you see STP in a problem, STP means 1 atmosphere of pressure and 0 degrees Celsius. All right, so let me join you on your note guide. Let's try a few practice problems. Let's see if we can convert based on the pressures that we learned about earlier, as well as these couple of temperature conversions. There are 2 here, and here's a third temperature conversion. Let's see if we can convert between units of pressure and temperature. Let's imagine that atmospheric pressure in Denver, Colorado is about 0.830 atm, right? And you'll notice that's lower than normal atmospheric pressure of 1 atm at sea level because Denver is at a high elevation. Let's figure that out in mmHg. So if we take our 0.830 atmospheres of pressure, we want to get that converted into mmHg, so we are going to do some dimensional analysis. But it turns out that all of these nice little pressure conversions that we gave you up in this table are conversion factors, right? They're all equal to one another, so if we put them on the top and bottom of a fraction, they become equal. So if you look at that table, you're going to notice that ATM and mmHg are indeed relatable, and it turns out that 1 ATM is equal to 760 mmHg. So if you do the math here and you solve, you will figure out that this is equal to 631 mmHg. You'll notice that ATMs cancel. You'll notice that we started with 3 sig figs, so we started with 3 sig figs here, 800 or 0.830. We ended, therefore, with 3 sig figs. You'll also notice that there's only 2 sig figs over 1 sig fig here. That doesn't matter because it's a defined conversion factor, right? So definitions don't count for significant figures. Let's take that pressure and let's convert it into kPa. And when we do the conversion to kPa, we have a choice. We could either start with 631 that we just got, or we could start with 0.830 because they're the same pressure, just different units. So you can pick either one you want. I'm going to pick 0.830. So 0.830 ATM. We're looking to convert that into kPa. Again, there's a relationship that you can find in your table between ATM, that goes on the bottom to cancel out, and kPa. And it turns out that 1 ATM is equal to 101.325 kPa. So your ATMs will cancel. You started with 3 sig figs. You'll end with 3 sig figs. When you do that math, you are going to get 84.1 kPa. And you'll notice that with all of these pressures, you can go direct from one pressure to another. It's not like you have to go, we just went from ATM to kPa. It's not like we need to convert ATM to mmHg to torr to PA to kPa. Nope, you can go directly because 1 ATM equals 1 mmHg. 760 mmHg. 760 mmHg equals 14.7 psi. You can go from any pressure directly to any other pressure. So let's do that. Let's convert this pressure of psi into pascals. So we have a pressure of CO2. We're told it's the critical pressure. We'll talk more about what a critical pressure is down the road. So the critical pressure is 1070 psi. We'll start there, right? We have to start with the number that's given to us. 1070 psi. We know that psi needs to go on the bottom to cancel out. We are asked to convert that into PA, or pascals. So there is a relationship between psi and pascals, and you'll notice in your table that 14.7 psi is equal to 1.01325 times 10 to the fifth times 10 to the fifth pascals. And so we can do that math, right? If we do that math, we will end up with 7.38 times 10 to the sixth pascals. And obviously here in Pennsylvania, we like pascals. So psi will cancel. We start with 3 sig figs. We end with 3 sig figs. We're all good to go. That's how we convert from one pressure to another. We also need to be able to do that with temperature. So imagine that we have a temperature of about 75 degrees Fahrenheit. So that's like a comfortable temperature outside, right? What if we want to convert that to Celsius? Well, there's an equation that we've given you up here that allows you to convert between Celsius and Fahrenheit. It's 5/9 times your Fahrenheit temperature minus 32. So if we plug in our Fahrenheit temperature, we will get the following, right? We'll get degrees Celsius is equal to 5/9 times our Fahrenheit temperature, which is 75, minus 32. That'll become degrees Celsius is equal to 5/9 times 43. And so really when you do that math, you'll get that your degrees Celsius is equal to 24 degrees Celsius. And 24 degrees Celsius can also be converted to a unit called Kelvin. So you'll notice up here that we gave you another conversion to convert to this unit called Kelvin. And let's talk about Kelvin for a second. So first off, if I give you a Fahrenheit temperature, in order to use this conversion, you have to convert it to Celsius first and then convert to Kelvin, because Kelvin equation uses degrees Celsius. And you'll also notice that we have to add, and so when we think about sig figs, we care about decimal place. So if we're trying to do our 24 degrees Celsius converted to Kelvin, really we want our Kelvin temperature to be 24 degrees Celsius, plus this number 273.15. But our measurement is only precise to the ones place, so our answer can't be more precise. Therefore, our answer simply becomes 297, ending in the ones place. You'll notice that we don't say degrees Kelvin, we just say Kelvin. So the temperature here is 297 Kelvin. The reason that we care about Kelvin is that Kelvin is the scale that includes absolute zero at 0. So 0 is the point on the Kelvin scale where absolute zero exists, and it's really the point where molecular motion ceases to exist. And so when we use gas law problems, we always have to use Kelvin, because 0 on Kelvin is where we don't have molecular motion, which means we'll never see 0 on the Kelvin scale. because when we put temperature into our equations, if we had a 0 for temperature, our entire equation would turn into 0, and that would not be helpful, right? So there's easily a 0 on the Fahrenheit scale, there's easily a 0 on the Celsius scale. This is why we have to use Kelvin for gases, because we don't want that 0 in the temperature place. So we will get very, very used to converting to Kelvin. You must always convert to units of Kelvin when dealing with